Right, okay, in this video we're going to look at utilising some of the skills and some of the equations that we showed you in the previous video. So I've pre-prepared a question on the board for you so you can have a look at this and follow through some of the calculations that you might be expected to do and variations thereof around springs and extension and the energy that we put into springs. So the situation that we've got here is we've got a mass of a spring of 50 grams. Here's the spring unextended. Its original length is 2 centimeters. We've got no mass on it, okay? No forces being acting on that spring, so it's unextended. So its original length is 2 centimeters. We then put a force on it of 4 newtons to extend it to 4 centimeters. So we're going to go through 4 things that we want to find out about this. The first thing is we might want to find out the force constant of this spring. Then we're going to have a look and see if we can find out the energy stored in this spring. Then we're going to look at the acceleration of the spring as we release the force, and then potentially a final velocity of the spring, maximum velocity of the spring as it rebounds into its original position. So we'll have a look at that. So the first things first, we're going to look at working out the force constant. Now, force constant is K. Now, in the previous video, we looked at F is equal to Kx, that's Hooke's law, where force is directly proportional to the extension. So, in this case, we can rearrange K to be F over X. Now, for working out the force constant here, you need to identify the values. So, we've got 4 newtons is our force. Our extension is 2 centimeters. Now, careful, if you thought initially that the extension would be 4 centimeters, you'd be wrong. It's the extension from the original length. So in this case, 2 centimeters more than what it was before, 4 centimeters. So we're going to be doing that, and putting that in meters is 0.02. Okay, and if we do that calculation, you should get an answer of 200 newtons per meter. Okay, so 200 newtons per meter. So this is a pretty stiff spring. Right, so that is our force constant. That's the first thing you'd be expected to do. Let's look at the next idea over here on the right. So the next idea that you want is we were looking at what is the energy stored in this spring whilst I've pulled it down. So the energy stored is, from the previous equation, energy equals a half kx squared. Or you could use half f of x. Either is good. I'm going to go with half kx squared just because I feel like you can usually use either, but if you were given one piece of information over the other, then you might decide to start with that equation instead. Here I could use half fx, but I'm going to use half kx squared. So k from the previous one is 200, so we can half that already to 100. We're going to then times that by our extension, which in this case is 0.02 squared. And when we work that value out, so 100, so 0.02 squared, and times that by 100, that's 0.04. joules. So that's the amount of energy that it's got stored in it. So that's the second thing we could find out. The third thing becomes a little bit more complex. So the third thing is the acceleration of this once we release the force. So once we release the force. So we've worked out that the energy stored over there is that. However, the force, we're going to use this idea to say that the force pulling it downwards is 4 newtons. Therefore, the restoring force, as soon as I release this spring, because the forces must be balanced, because it's not accelerating in any way, we'd be expecting, while I've got 4 newtons on here, that there would be a 4 newton pull on this. So, and that's the restoring force for the spring. Once I remove this force, that 4 newtons then springs into action. The forces are unbalanced, it accelerates. So force is equal to mass times acceleration. So the acceleration of this spring initially would be F over m, which, as we know from the calculation, from the beginning, we know that the mass is 50 grams, which is 0.05 kilograms. That's divide that by the mass. Apologies, I've done that the wrong way around. Sorry, 4 newtons over 0.05. And we work that out. We should get 80 meters per second to the minus 2. That's the initial acceleration of this one right here. Okay then, finally we're going to look at working out the maximum velocity that we can obtain. And we're going to need that energy up over here. So, that is the maximum energy that it has. Now we can assume when we release this, all of that energy, stored energy, is transferred into kinetic energy. So we can say that 0.04 joules is equal to a half mv squared. Therefore, the max possible energy velocity we could have is v is equal to the square root of 0.04 times by 2 divided by the mass, which is 0.05. And when we work that out, we should get an answer of 1.26. So 1.26. So that is the speed, and those are 4 calculations that you might use to do around springs.